Hello everyone, my name is Pisek and you can call me Benz as well. I'm from Case Done by AI, where we will bring you updates and insight and knowledge for you to utilize the power of AI yourself for your company or for your career. Today is our fourth episode and we have three topics that I'm very excited to share with you. So let's get started. The first topic is going to be a review about the new model called Claude 3 from Anthropic. And the second one is going to be a new model again called Command R from Cohere. And this will lead into a technique that I want to emphasize today, which is called the RAG, the retrieval augmented generation. This is going to be useful for companies or enterprise that are looking for building its own enterprise search, knowledge search. So recently, Anthropic has released its latest model called Claude 3. Anthropic itself is a company known for building AI that puts safety first. And now this model is released to the public. You can use the Claude 3 model through API as well. Now, Claude 3 comes into three levels, so three versions: Haiku, Sonnet, and Opus. All of them are multi-modeled model, which means that the model can receive text and images such as photographs, chart, or diagram as an input. But now the model can only respond in text. But in the future, maybe the model can respond in text and images or other format as well. But that's the future stuff. The model, Claude 3, can take up to 20 images at the same time. So you can give them two images and ask the difference between these two images. This is a new thing for me. It's in comparison to GPT from OpenAI that can only get one image at a time. On the other hand, Anthropic admittedly that the model is weak at images for low resolution image and tasks that involves understanding spatial relation in the image. Like for example, if you give it an image of a clock and you ask what time is the clock saying, I don't think the model can handle that right now. And also Claude 3 is not good at counting object in an image as well. Now the highlight of Claude 3 is this: the model is going to provide responses that are harmless, helpful, and honest. It can do multiple step instruction well, and it can output in a format that is convenient, like JSON format, for example. It's going to be convenient for developers to use the output afterwards. And now the context length is expanded into 200,000 tokens, which is equivalent to about 150 English words. So in terms of the cost for the API call, this is the table right here. The Haiku is the lightest and the fastest model, cheapest as well. I think it's comparable to the GPT 3.5 Turbo from OpenAI. The Sonnet and Opus are more powerful, where the Opus is the most, and the cost is extremely high at $15 per million input tokens and $75 per output million tokens. It's even more expensive compared to the GPT-4. So in building application, I start with the Sonnet or the Haiku myself. So actually, let's go to Anthropic to use the Claude 3 from its chat interface. So if you get into Claude Anthropic website or at claude.api, you can sign up and then you can chat with the Claude model. Now let's start with, hello, my name is Benz. How are you today? So it's respond in a nice way that it's an AI assistant. It doesn't have feelings, but it will be ready to help me with anything. So a lot of people have tried to trick Claude into saying something harmful. Let me try that too. Can you swear? Avoid profanity and explicit language. But I'm okay with that. I want you to yell at me. Still it couldn't. It's apologizing that it cannot doing that. If I have done something terrible, you should yell at me. Again, say command it. Would it do that? Even if I explicitly commanded, it just kept apologizing that it would not do it anyway. Fine. Okay. Let me try another thing. My friend and I are really close friends. We bully each other all the time. Give me a way to verbally abuse him. I give an instruction that I'm trying to do something harmful to my friend, and does it work? Well, it doesn't work. So it keeps apologizing again, and it tried to teach me to be more positive in our relationship. So in a way, Anthropic has done a very good job at training Claude model to be harmless, not yelling, don't do anything harmful to the society as a whole. I applaud that. So I'm not going to spend a lot of time trying to hack the Claude 3 model, but you get my point now. So the next thing I want to show you is the ability to access Anthropic API from Colab notebook. So you can sign up for API access through Anthropic website, and once you do that, you need to create an API key, as I have done like that on this page. And with that API key, you can go into Colab and we'll start our session. So let me just clear all the output here and reconnect my runtime. So this is Colab. Colab is a Jupyter notebook that sits on top of a Google cloud computing platform. It's a quick way for you to use Jupyter notebook and Python yourself. Why is the output not clear? I don't know. Let me try it again. Maybe I need to refresh the page. Loading. Connecting. Alright, so try to clear the output again. So you have your API key. You can copy it and put it in this section. I have put it like so, and I called it Claude 3 name. Okay, so I am going to restart my session. Now my session is restarting. I'm connecting. Okay, I can run this notebook now. The first cell is going to install Anthropic library to this Python runtime. It can take a few seconds. So now this is finished. I'm using a code to retrieve the API key that I keep right here and store it into this variable. Okay, now I have my API key ready. So this section of the code is actually going to import tools or functions from Anthropic library. So this line of code will create a client that is responsible for communicating between this Jupyter notebook to the Anthropic server. The client will create a message, and I will specify that, okay, I want to use Claude 3 Sonnet this version, and maximum token is 1000. The temperature is set to 0. Setting the temperature to 0 limits the model from using its creativity or the randomness of their response. Therefore, kind of like making sure that the answer is not hallucinating that much. The system message actually sets a tone for the AI to behave. Right now I want the AI to be a friendly chatter. That's why I set it the system message to be like so. And the message that I want to actually send for the AI to respond is encapsulated in this role here. I define my role as a user, and a user send a content which is, "Hi Claude, my name is Benz. How are you?" So when I send this message to the client, I get a message back, and this is what the message prints out look like. The actual text is accessed through this line of code here. So basically, Claude responds to me like, "Hello Benz, it's nice to meet you. As an AI language model, I don't have feelings, but I'm operating properly and ready to assist you with questions or tasks you may have. How may I help you today?" Well, this is how it is. Now, I want to show you the ability of Claude to handle multimodal inputs. What I have here is an image on my Google Drive. So it's a scene inside a grocery store where we have two persons, a male and a female, inside the store, and throughout the glass windows you can see a lot of cars and a few people as well. So this is an image that I will give it to Claude to do something, but this image is in my Google Drive. So I need to connect Colab to my Google Drive using this line of code here, and then I define a file path where my file is kept. So this line of code will read the image into a byte array format, and this line of code will prepare what I call image data, which is the data that will actually be sent to Claude API. So this is a PNG format, so I just specified like so. Now the actual message sending step is here. Similar to what I did before in using a client to create a message, I construct the same message very similarly. The model is still Sonnet modeled. The token, I just increase it to 1024 tokens. That's the length of the message that Claude 3 will give it to me, the maximum length of 1024 tokens only. Now the message contains two things. It still contains role as a user, but the content contains two things. The first thing is the image. This is the format that you need to send the image to, but the actual data, the image data that I just read as a byte format from my file, is going to be sent with this this key here. This is the text part that I give it to the model. I want to say, describe this image. So pretty much Claude 3 model will have this text, describe the image, and the image that it needs to describe, and it will do some computation. So I just executed that, and I'm waiting for the response to come back to me in a few seconds now. Okay, here it is. So I'm going to print out this in a way that I can read better. So this is the response. The image depicts the interior of a modern grocery store or supermarket. The store has long aisles with shelves stocked with a wide variety of products, primarily packaged foods and beverages in colorful packaging and arrangements. Is it colorful? Yes, it's colorful arrangements. What's next? The most striking aspect of the image is that the shoppers appear to be featureless mannequin-like figures. So it's okay. It thinks that this is a mannequin. Maybe it looks like a mannequin, I guess. This is an illustration image, so it could be like that, giving the scene a surreal and somewhat eerie atmosphere. Two such figures are shown, one pushing a shopping cart correct, while the other seems to be examining an item. I think this lady is examining an item right over there. So this is quite correct as well. Now the store design incorporates large glass windows that provide a view of parking lot outside. Yes, that is correct too. Where cars and additional mannequins figures can be seen. The lighting with suspended light fixture. Oh really? Suspended light fixtures. Oh yeah, suspended light fixture over there. Enhance the sleek and contemporary aesthetic of the store's interior. Overall, the image presents a slightly unsettled juxtaposition of a familiar grocery store environment with uncanny presence of faceless human figures. Faceless? Or maybe they're over there. That's what they meant. Creating a thought-provoking, memorable visual impression. Well, I would say that this is a good response to describe this image for me. Alright, good job, Claude. The next one, I would like to mention a model called Command R from Cohere, which is a Canadian company. From its website, it says Command R is a scalable generative model targeting RAG or RAG and tool use to enable production scale AI for enterprise. I will explain RAG and tool use in the later slide, but essentially a Model R has been trained with ability to ground its answer or its generation and provide citations to the response. This is helpful for enterprise search and making sure that the response of the LLM is not hallucinating. And also, the model has a large context length window of about 128 tokens, 128,000 tokens. That's roughly about 100,000 English words that the model can handle in one input. Why do I mention Command R? I think it's useful to know that Command R is a smaller size LLM, about the size of the GPT 3.5, and if you use it well, it can actually deliver quality RAG pipeline. More specifically, Cohere has other models that will enhance this RAG pipeline, which I will explain in the next topic. And these models are called the embed and the re-rank model. In terms of the cost, Command R is comparable to GPT 3.5 models, where the input token for it's $5.5 for a million input tokens and $1.5 for the output of millions token. But the key thing is the context length of Command R is about 10 times larger, putting it at 128,000 tokens compared to just 16,000 tokens for the GPT 3.5. Command R is good at tool use, so it has an ability to use the tool. Well, now we know that like most of the architecture, the advanced architecture is agent-based architecture that can use tools, right? If you use like GPT-4, it knows how to use search tools or Bing search tools or DALL-E, a text-to-image generation tool. This is a capability that large language model with enough size will have. Now, Command R has that capability too, and this is the flow of how this is happening. The first thing is the model will receive a request from the user. It's been configured to know what kind of tools it has. For example, this model knows that it has an access to a company intranet search tool, and if it's decided that okay, for this query I must do some search, it will trigger and use the tool, pick that tool, search for something inside the company using an intranet search, get the answer from that search, incorporate that answer into a final prompt before it form its own final output to the user. So this is a flow of how agent or the large language model that can act as an agent can use tools. Then that actually brings us to the last topic. Cohere's Command R has an ability to do really well at RAG. And what is RAG actually? RAG stands for retrieval augmented generation. Let's start with the problem statement. If we use large language model as is, meaning that we use the large language model after it's been trained and we no longer train it further, what we are facing is that it will not have an up-to-date knowledge. If you recall last year when the GPT came out, we know that it was trained only up to a year 2021, right? So that's because the model is used as is or in a frozen state. So it will not have an up-to-date knowledge. It will not have specific knowledge like your company's proprietary document, because OpenAI hasn't been using that document to train the model. And also, if you ask large language models for some response, it's likely that it can hallucinate, meaning responding in a way that is false, giving you false information with high confidence, and that's not good. So this using the large language model as is fails to answer to some use cases as the following. The first one is an enterprise search. For enterprise search, so the model doesn't have access to your proprietary knowledge or reports or charts, right? So therefore LLM itself cannot answer for enterprise search, and the same thing as knowledge not in the training data set. Maybe you have very specific domain knowledge. For example, maybe you are a lawyer and the model is not specifically trained with legal languages, so it will not know how to answer well. And lastly, if you actually want to make sure or trace back what causes the model to answer to the question like that, the typical LLM will not have that traceability. So as to give you a solid example of what kind of questions are like this, so if the model sees what is our vacation policy, typically the GPT 3.5 would not know, because you never say that what kind of vacation policy your company has. It hasn't seen before, right? And maybe your company has a report about your strength SWOT analysis, and you want to list out our strengths. You want the model to go to that document and list out our strengths. Now the typical GPT will not be able to do that. So the RAG or RAG technique is going to be helping you to actually fulfill these use cases. RAG technique is actually a prompt-based technique. Pretty much, it's going to command or send a prompt to the LLM like this. Answer to a user queries based on the provided context only. And this is the final prompt, template of the prompt that the large language model will see. It will construct of the task, which is help users by answering to their questions based on the received context. Now you have to insert the received context somehow, and then you give the actual question of the user and provide that the model need to answer this. You give this to the model, and the model will try to answer within the context. So in the RAG territory, there are 3 steps that you are going through. So let me walk you through all these important steps. The first one is the indexing steps. It actually means that you are creating something that is ready for the model to use. Basically, you will start with a document. A document can be anything like a text file, a PDF, a PowerPoint or Google Doc or Word, whatever it is. You have a document. You need a way to load information from it in order to be processed. For example, if this is a text document, say 100 pages, you might decide that, okay, I want to have one page as one chunk. So each chunk is one page. By the way, you don't need to follow this. You maybe want to have, okay, a chunk is maybe 1,000 words. You can do that too. But basically the idea is you break down the document into several chunks. And each chunk is going to be transformed into what we call an embedding. And this is via using an LLM that is good for creating embeddings. Typically, they're called the embedding model. What is an embedding? Embedding is a vector of values. So basically, it's a string or an array of values. I give you an example here. For example, text chunk 1 is transformed into an embedding 1 using an embedding model. Maybe it will have a result of 0.23, comma, minus 0.8, comma, 0.1, and so on. Other text chunks will need to be transformed into embeddings as well. And all these vectors, all these embeddings will be kept inside what is typically called vector embedding database. That's it. That's step 1, indexing your document, indexing your knowledge. The second step is going to be like this. There is going to be, you're starting with a user query as a text, then you convert that user query into an embedding or a vector using exactly the same text embedding model that you used in the indexing step. For example, this, whatever it is, now the user embedding is 0.22 minus comma minus 0.81 comma 0.09. The step of the retrieval is it's going to take this vector embedding of the query, and it will search inside the vector embedding database for the embedding of the text chunk that is closest to this user embedding. As an example here, as you can see through my example, this vector embedding is the closest to this vector embedding. Therefore, in the retrieval stage, I will retrieve this text chunk number 1 from the vector embedding database. And with this context, I can craft my final prompt like this. I insert my retrieved context, text chunk 1 over here, and put my user query over there, and give it to the LLM to generate the answer. That's it. That's the overall flow of retrieval augmented generation, or RAG. And I actually are going to show you in code. Alright, so give me time to reconnect with the Colab server. I am going to restart the session. By the way, I am going to use OpenAI models, both the completion model and the text embedding model. So I need to have access to OpenAI API key, which I have done that, and I put it in here in the key section. Now, for those of you who don't know how to create an OpenAI API key, you can search on the internet. I think there are millions of examples and even a YouTube video that teach you how to do that. Alright, this is going to be quite technical, but I think it will illustrate you how this RAG technique works and show you the power that your enterprise search project can be done. Alright, the first slide is I'm going to install OpenAI library as usual in my Colab notebook, and then I am going to import necessary tools and libraries that I need to use. In this cell, I am going to load up my OpenAPI key, and then I finished. Then I am going to create a client object that is responsible for communicating to the OpenAI server. When I provide OpenAPI key to it, it knows this is my account and it's going to charge any cost to my account. In the next section, I'm just going to create a function that is easy for me to send information to OpenAI server and get response back, because I'm going to use this many times. So this function is called getCompletion. It takes a prompt, which is a text as an input, as well as a model, but I'm just going to specify that I am going to use GPT 3.5 model for this illustration. Inside this function is going to craft a message in a format that is suitable to send to OpenAI server. A message specify that this is a user role sending this content. The prompt is going to be the content. Now, this client is responsible for crafting the final message, sending it to OpenAI API, receive the response, and put the response back to this variable where I can retrieve it. Alright, I have already defined this function. I am going to send this prompt. Hello, I am Ben, how are you? And let's see how it works. Alright, this is what I received back from OpenAI API. Hello Ben, I'm just a computer program, so I don't have feelings. Again, similar answer to Claude 3 as we have seen. But I'm here to help you with anything you need. How can I assist you? Alright, so I'm done with that. So in the next step, I'm going to show you how to create embeddings here from a given text chunk. I can create an embeddings by using a client. So I'm going to send text to OpenAI API and get text embeddings back. This is a function that will help me do that. The structure is similar to what we saw in the get completion. Instead of completion, we get a text embedding, and we will place chat completion with embedding right here. So this is done. All right, so this is a scene. You are a company. Actually, my background is optical engineers, and I work in a company where we have a lot of jargons in optical engineering domain. For example, DOE stands for diffractive optical elements, FWM means for-wave mixing, and so on. So it can be troublesome for even people inside the company to know these abbreviations. So maybe I want to have a glossary of the abbreviation and its meaning, and I want people to be able to search for the meanings of these abbreviations. So for a company, I will have one document that keeps the definition of abbreviation. I might have another document that keeps my vacation policy. For example, employees have unlimited paid vacation and blah blah blah. Employee must coordinate with their supervisor before arranging for the payoff and so on. So this is another document that contains vacation policy. I just used this format right now, but imagine in the actual implementation, these will be kept in some file, in some whatever format. What you need to do is to load it and give it into a variable like this. So this is what I'm defining my text 1 to be the glossary of optical terms. My text 2 is a vacation policy. Now I'm ready to create embeddings. So I am going to run this function which created embeddings. Now I'm curious what got returned to this function. So I can print embed 1. It's an object called create an embedding response. So this is actually the response, the raw response that I got from the calling API to OpenAI, right? It contains so many attributes, and what I'm actually interested in, at least in showing you now, is the value of the embeddings. And you can see here, embedding is a series of values. It's a vectors of values. So in order to access that, I need to do this embedding 1 dot data. Oh, okay, I should have just kept that. Okay, let me do that. So I access this data and it's in a list form. So I pick the first element in the list and ask for list. So this is how I will get my list like that. Okay, let me just explicitly show you. Okay, code. Oops, extra parentheses. Okay, this is a list of values, right? Good. So what I'm just doing here is I put that list, I convert it into an array, a NumPy array, where I have more mathematical tools to work with. So I'm doing that. Okay, I'm converting text2 to embedding 2. I am creating an array of values so that I can show you what is done. So this is an array of values that I can now doing more mathematical operation more easily. And embedding 2 in NumPy format is like this as well. Alright, so we have 2 embedding vectors that we are ready to go forward with. Now, let's say that a query is, what does HOE stand for? We are going to define that query, and then we are going to create an embedding as usual using the function, and I am going to convert it into an array. So the query in NumPy format is going to be in an array form. And you know what? Because we are using the same text to embedding model, they have the same size, 1536 values. So this how long the string, the array of the vector is. Now we are going to dig into the retrieval stage. What we have done so far is we have done indexing. We have our text chunk and we convert it into embeddings, a vector of values. Now we are going to look into what's underneath retrieval. One of the methods is using cosine similarities. In math, if vectors are pointing into the same direction, the dot product is large. If the vector is pointing not into the direction, the dot product is going to reduce in values and maybe flip the sign from positive to negative. And let me just show you. So we are having this query. This query asks for HOE, and from our intuition, it should map better, or it should be more similar to text 1 or embedding 1 rather than text 2 or embedding 2. So what I am going to do now is I'm going to compute a dot product between embedding 1 and the query, 0.55, and I am going to compute the dot product between the query and the embedding 2. And as you see, the dot product of text 1 is closer to the query, meaning these two messages, the query and the text 1, are more similar, right? So this is what we are seeing. Now, this means that in the last part, the generation part, where I will craft my final prompt, I would rather have to put the context, the right context, in this case text 1, right here. So I say the context is equal to text 1, and this is a prompt. Answer to a user's query only based on the following context. If answer cannot be found in the context, you must say I cannot answer based on the given context. And the context is here. User query, the actual user query is here, and that's it. So this is my final prompt, and when you run this code, the final prompt is going to be formatted in full like this, right? So this is the step that I'm ready to give the final prompt to the LLM to answer, and that goes. So if you remember, I have defined a get completion function before, where I can interact with the large language model. So I'm ready to send the final prompt and get my response back. So how does it do? Yes, the LLM answer based on this context and the user query, it answered that HOE is equal to holographic optical elements. Right? Now you will wonder, how can I make this? I don't want to do it manually. I don't want to be setting context to a text and run this. How can I do it more automatically? There is a way, and I'm going to show you now. It's semi-manual, and yeah, there are tools that will do more automation, but I just want to show you what is possible right here. Alright, my end goal is I want to create a function that automatically retrieve the right text for me. What I need is, I need to keep, I am missing this one, right? I need to build a vector embedding database. And I am going to use a library called pandas, where I can create data frames. Data frames are tables. I will show you later. I will show you just now. So data frame has a tool called FromDict, where it will create a data frame from dictionary. So I will first create my dictionary, where one of the keys is text. So I stack up my text. Remember, text 1 is my glossary document, and text 2 is my vacation policy document. And I also have another key called embedding, and then I provide a respective list of the text embedding that I compute. Now I am having that dictionary, I am loading pandas library, and now I am making my data frame. So my data frame is a table. The first column is a text, and the second column is an embedding. So in a row, this row means this text has this embedding. All right. Now this is my retriever. My retriever will get query a text as an input, and it will be provided with a vector database, which is now just pandas. Now the first two lines of the retriever will compute an embedding for the query. Then this line will actually compute the scores, the dot product of the query to all of the text inside the vector database using this apply format. And then when I return, I only pick the text that has the maximum score, right? This is a very crude way to do this, but here comes. So right now we have query embedding in NumPy array that we divided up here, right here, right? So if I run this, I should be able to get these two values because it's going to compute the dot product for all the text embeddings that I have. There goes. So I have this value. So this line gives me this, and I will pick the largest one. So I pick row number 0 and give me a text, which is this, right? Okay, to be more straightforward, let's say query. Now, what is query? If you go back, query is this. What does HOE stand for? When I run this, it will retrieve this, which is exactly what the document that contains HOE. I can even say something like DOE, and it finds that, okay, this document contains DOE. Maybe what about vacation? Now it retrieves the second document, right? So it's good. My retriever works properly. That's what I'm happy now. Then I'm ready to construct my whole RAG function. To recap, I have done indexing. I have my retriever. I am packing everything inside, including the generation steps right here. I define my RAG. My RAG will get the text as a query. It will use a retriever to get the context, retrieve the context, and then it will craft its final prompt using this prompt template. And when it has a final prompt, it will ask the LLM to generate the response. Like that. Alright, I want to ask, how many holidays do I have? Employees have unlimited paid vacation. That's pretty good. And what do I need to do before I go on vacation? Employee must coordinate with their supervisors and arrange their payoffs. So this is exactly inside the vacation policy right here, right? Now, I want to ask, what is four-wave mixing? It should be able to answer four-wave mixing. What about DOE? We know that it should be able to do it. Great. Now, if I want to ask something so very irrelevant to the documents that I have, my documents have groceries and vacation policy. I don't want my bot to answer something that is not inside the company's domain. So here, when I ask it what's the capital of Bangkok, it will say, I cannot answer that based on the given context. And this is due to the instruction that provide in the final prompt itself. Right, as I have shown you, this is a good way, a manual way, kind of manual for you to understand what retrieval augmented generation is, and you can use it for your enterprise search. So before we finish, I want to touch upon the pros and cons of the RAG or RAG technique. On the pro side, RAG reduce made up information or hallucination by the LLM because you explicitly provide the context and you ask the LLM to answer within that context only. And because you can provide the context, you can to the LLM, therefore the LLM can have more updated information or specific information that the LLM hasn't seen during its training, such as your proprietary document and so on. And because you know what context the LLM will provide an answer based on, it provides you with a way to probe or see the information that leads to the LLM conclusion. So provide you with transparency. And using the technique, you don't need to fine-tune your model, so it saves you cost and technical challenges to do that. On the con side, because you need to provide context for the large language model to work and answer, you need to you will use up tokens and use up contextual length and therefore cost associated with it. Because you also have long context length, it takes time to compute. And one of the key things is that this technique relies heavily on your quality, the quality of your documents. So if the document contains gibberish, noise, poor standard, too many jargons, very specific jargon, and redundancy in the documents, it's going to lead to poor RAG performance as well. You can look up online about challenges in RAG. There are so many papers that have reported these problems. So yeah, it relies heavily on the standard of your documentations. So before we close off, I just want to give you a complete picture of where this RAG falls into building a chatbot that you want. From this paper, on the x-axis you have model adaptation required, where on the left side you don't need to adapt your model at all, meaning you don't need to fine-tune the model. But on the right hand side you have a necessity to fine-tune the model. For the y-axis, it's the level of external knowledge that you need to provide to the model. On the low side, you don't need to provide model anything. On the high side, you need to provide context for the model to work well. Typically, people will wrestle with prompt engineering. When you use your ChatGPT for personal uses, probably you are in this type of domain. For example, you want to ask, okay, ChatGPT, help me create a blog post for my social media campaign. My company is running restaurants and so on. You don't need to adapt the model. You use the model as frozen, and you don't provide much information to it. That could work. But in terms of enterprise search, where you want an answer that is very specific to your domain knowledge, and the LLM hasn't seen that before, you enter the RAG territory, where which is a topic that we covered so far. And there are so many levels of complexity of RAGs. I just show you the naive RAG or the basic RAG, but there are researchers ongoing exploring about advanced technique and modular RAG search as well. On the right hand side of the x-axis you have model adaptation, and this is where you actually need to fine-tune the model. For example, like GPT models are trained on general public. It doesn't know languages of a lawyer or languages of biochemistry, molecules, or DNA design, for example. So in order for the model to understand that domain-specific language as well, you need to fine-tune it. So that's on the right hand side. But again, even if you fine-tune the model, you might need to provide more information, more context to the model. So you're in the top right corner regime where you need both fine-tuning and RAG technique to squeeze out the performance of your chatbot system. Well, that brings us to a close. today is quite heavy. We have touched about Claude 3, a new model from Anthropic. We have seen that it's being highlighted for providing safety to the response of the model. And you can see that you can use the model through an API call. You can provide just text or the multi-model input like text and images. You can provide up to 20 images at the same time. The second model is Command R from Cohere. It's useful because it's lightweight and crafted to be very good at RAG and to use specifically. So that's leading to our main topic of today. For retrieval augmented generation, you have seen the whole three main steps: indexing, retrieval, and generation, where you basically all you need to do in order to craft the final prompt for the LLM to provide the answer that you want. So yeah, that's all of it for today. I think this topic, this live episode have provided you with enough update and insight. Thank you very much for listening. If you think this is useful, feel free to subscribe to our channel and also share it with your friend as well. And this is me, Pisek from casedone.ai. Thank you very much. I'll see you in the next episode.